In our last video, we talked about pH as a way we measure acids versus bases. But now comes the math. We can actually calculate pH. So to help deal with small numbers, scientists came up with the pH scale. Because in reality, what we're talking about when we're measuring pH is incredibly small. So the pH scale actually evaluates the concentration of hydronium ions. Remember, that is H3O+. Oftentimes, so we just think about it as H+. We use square brackets, like you see on your screen, to indicate concentration. The pH scale ranges from 0 to 14, as we mentioned before. And because it's a scale, pH does not have any units attached to it. It is just what it is. So to calculate pH, we use the negative log of the hydronium ion concentration. We can also calculate the hydronium ion concentration by doing 10 to the negative pH. A lower pH value, as you already know, is more acidic, which means it has a higher concentration of hydronium ions than a higher pH. Remember, hydrogen ions and hydronium ions can be used interchangeably. And here is just a diagram of the pH scale for you, showing you that pH 2 is 10 to the negative 2, just like we talked about over here. So let's do some practice problems. You are asked to find the pH of 0.0025 moles of hydrochloric acid solution. So we know that HCl is a strong acid and is 100% ionized in water, as we already learned about. So therefore, we know that the hydronium concentration is 0.0025. So we are going to take the pH equals the negative log of 0.0025, and that's going to work out in our calculator to 2.6. Once again, no units because pH doesn't have units. Remember, we can also do the reverse, where if you were asked what is the concentration of hydrogen ions in a solution that has a pH of 4.3, we can use our formula where hydrogen ions equals 10 to the negative pH. So I make 10 to the negative 4.3, which was the pH I was given, and it's going to come out to 5.0 times 10 to the negative fifth. Now you will notice in both cases I use sig figs, where my starting number had 2 sig figs, so my final number had 2 sig figs. Once again, starting number had 2 sig figs, so my final number had 2 sig figs. Now we can also calculate pOH, which is like the opposite of pH. So a similar logarithmic scale has been calculated for the concentration of the hydroxide ions, which we talk about in terms of bases. But most solutions do have both in them. Luckily for you, they are the same formulas, where pOH equals the negative log of the hydroxide ion concentration, and the hydroxide ion concentration is equal to 10 to the negative pH. The pOH can also be calculated just like we calculated pH. Once again, that same scale for you, where this time you may notice that you didn't before, that we have that hydroxide ion concentration working the same way. So let's practice calculating those. First, you were asked, what is the pOH of a solution that has a hydroxide ion concentration of 4.8 times 10 to the negative fifth molar? Once again, pOH equals the negative log of the hydroxide ion concentration. So that means we're going to make our formula negative log 4.8 times 10 to the negative fifth. And when we enter that into our calculator, we are going to get 4.32. Once again, you will notice that our number we started with had 3 sig figs, so our answer now has 3 sig figs. We can also do the other type of calculation, where you are asked what is the concentration of hydroxide ions in a solution that has a pOH of 12.2. I'm going to use the formula, the hydroxide ion concentration equals 10 to the negative pOH. So 10 to the negative 12.2. We are going to get an answer of 6.31, 3 sig figs, times 10 to the negative 13th. See, these calculations aren't so bad. I know you can do them, just have to enter it right into your calculator. Now there is one last way to calculate pH and pOH that we haven't talked about yet because they're connected to each other. So the pH and the pOH, or the concentration of hydroxide ions or the concentration of hydronium ions, can be determined using the following equation. pH plus pOH equals 14. This handy equation allows us to connect pOH and hydroxide ions to pH and hydrogen ions. So a simple example, a solution has a pOH of 11.76. What is the pH of this solution? So that means pH plus 11.76 is 14. So after some subtraction, we're going to get that the pH is 2.24. Now I know some of you at your computer are celebrating because you think Miss Hinkson just did her sig figs wrong. But she did not. Remember, when it comes to addition and subtraction, you do not care about the overall number of sig figs, but only care about the numbers after the decimal point. So 11.76 had two numbers after the decimal point, so therefore I have two numbers off after the decimal point, indicating the correct number of sig figs. So now that we know how they're connected, we can actually tie more than one of these formulas together. Let's do an example like that. So you are asked, what is the hydrogen ion concentration when the pOH is 5? So up first, we take pH plus 5 equals 14. By doing subtraction, that allows us to know that the pH is 9. But the equation was not asking us about the pH. The equation was asking us about the hydrogen ion concentration, which means we're left to use the hydrogen ion concentration equals 10 to the negative pH. So we plug in our 9 into that equation, and that means we are going to get that the hydrogen ion concentration is 1 times 10 to the negative 9th as our answer. So it takes what was a one-step problem into a two-step problem, but opens up a world of possibilities. Now we have ways of testing for pH. We're going to be practicing with one of these in class. We have pH meters and probes, which we will be using, which allow you to electronically determine pH. They give you a readout kind of like a thermometer. We have pH paper and litmus paper, where pH indicators use color to indicate the pH. You probably used these in biology last year, where you dip the paper in and it turns a color. You compare that color to a chart to determine what the pH is. Then we also have liquid indicators that you can see in this chart below that will change different colors depending on the pH. Now, one liquid indicator is not necessarily good for everything, so you can see on this chart how depending on what we're trying to test for, we may use a different color and a different type of indicator. So this brings us to something called neutralization reactions. So when an acid reacts with a base, a neutralization occurs. In a neutralization reaction, water and a salt are always produced. Keep in mind, when I say a salt, I don't just mean sodium chloride, although that is a salt. All of our halides produce salts. A neutralization reaction does not always result in a pH of 7. 7 is the neutral pH, but neutralization reactions will not always, they sometimes will, but will not always create a solution with a pH of 7. It's just going to result in a more neutral substance, but not always completely neutral. So let's look at what that means. So when a strong acid reacts with a strong base, it is going to produce a mostly neutral salt and water. So it's going to be pretty close to that 7. Example, sodium hydroxide, strong base, plus hydrochloric acid, a strong acid, produces water and sodium chloride, salt and water. However, when a strong acid reacts with a weak base, it's going to produce an acidic salt and water, meaning that your ending solution might still be slightly acidic. When a strong base reacts with a weak acid, it's going to produce a basic salt, meaning your resulting solution is still going to be basic. And when a weak acid reacts with a weak base, it can produce a neutral, acidic, or basic salt. It really depends on the specific acid and base that are being reacted with each other. So they're a little unpredictable. This brings us to something called titrations, which you're going to be performing a version of a titration in class. A titration is an experimental way to determine the concentration of an acid or a base. A neutralization reaction that reacts an unknown concentration of acid and base with a known concentration of acid or base. And you do this until you reach the end point. And this is the point at which a titration is complete. At the end point, your indicator will change color. Data is then used to create a graph, which we call a titration curve. The equivalence point is the point at which there are equal moles of acid and base. This is shown on your titration curve when it creates an up and down vertical line. The titration curve is used to calculate the concentration of the unknown acid and base. This is the setup for a titration. We're not going to be doing exactly this, but we will be doing something similar. You have your Biuret clamp and your Biuret over an Erlenmeyer flask that contains a solution. We slowly add from our Biuret until we get this light pink color, indicating that our titration is complete. Now here are some titration curves for you to view. You can see how the equivalence point is different depending on what we are reacting. So you remember earlier when we reacted a strong acid with a strong base, sodium hydroxide is a strong base, it produced at its equivalence point essentially a pH of 7, neutral. On the other hand, when we still have that strong base, but we react it with a weak acid because it's producing a basic salt, that equivalency point moves to 8.72, which is basic and not neutral. You can see the equivalency point in both is halfway up the vertical line that is created in the graph. You are going to be experimentally creating one of these graphs in lab. The last thing we want to talk about is buffers. A buffer is a solution that resists change in pH. A buffer consists of a weak acid and its conjugate base in equal amounts. The buffer solution is continuously converting between acid and its conjugate base to keep the pH of the solution the same. So we use it to maintain a stable pH. There are lots of examples of buffers you are familiar with. Your blood is actually an incredible buffer. It resists changes to pH, which is really good for you because you don't want your blood up and turning into like an acid on you and burning through your skin. Also, if you've ever heard of buffered aspirin, what they mean is it's literally covered in a coating that is a buffer to prevent it from changing the pH. So there are lots of examples of buffers you are familiar with. All right, that's all I got for you. Have a great day.